In this series, we're talking about conducting a regression with mixed variable types, both categorical and quantitative explanatory variables, when we have a single quantitative response variable. And we've been working through an analysis of covariance, or ANCOVA, example. Now I want to pause for some very important information, and that is the conditions that we need in order to have a valid interpretation and valid inference with analysis of covariance. I have an asterisk here by inference, and I put an asterisk next to those items that are about inference rather than interpretation, and the other items are about interpretation, which of course then also means inference, because if you need it for correct interpretation, you certainly can't infer outside of your study based upon not having a correct interpretation. So you really can think of inference as all of these bullet points, but only inference is for the first 4 of these bullet points. And these should look familiar to you. You need independence of observations within groups. You need independence of observations across groups. So for the grouping categorical variable, it's a between subjects factor. The observations in each group must have the same variation because, as you know, we're going to do an analysis of variance in which we have a single mean square for the residual, and that single mean square for the residual is estimating the variation in each of the groups, and so therefore the observations in each of the groups need to have the same variation for that to be a valid estimate. Also, the residuals need to be normally distributed in order for us, when we're calculating critical values for any inference, to be using the correct distribution. So residuals are normally distributed. So those 4 are about inference, but this list keeps going for things that are also about, in addition to inference, about interpretation. The covariate is not related to the explanatory factor. So in our example, we've been using an education covariate and a race for the explanatory factor, and in order to make valid interpretation, you cannot have the races have these intentional differences on the covariate. I mentioned before that I often see analysis of covariance that's done incorrectly, and this is probably the main culprit. When people will do analysis of covariate intentionally because the covariate's related to the explanatory factor, because they see individuals in one group at a different level on the covariate than another group, and they think that by using analysis of covariance, they can somehow adjust these, ignoring the fact that in order to do that, you're going to be making extrapolations outside of the range of the data that's within each of your groups. So you can't have the covariate related to the explanatory factor, unlike what you might read with some people that that's the time to do analysis of covariance. It's just the opposite. That is not the time to do analysis of covariance. We are hoping for the covariate not being related to our explanatory variable. That's why when I looked at education level for the different groups, I was hoping that we had similar education levels across the different groups. Then within each group, so in our case within each of the racial categories in the example we've been working through, the relationship of the response variable and the covariate must be linear. The relationship of the response variable and the covariate. So in our example, the response variable is income, the covariate is education. So there's a relationship of education to income. We want that not only to be linear, but to be linear within each of our conditions. And then look at this final bullet. The relationship of the response variable and the covariate is the same within each group. So not only do we have a linear relationship, but that linear relationship must be the same so that when we look at the relationship of education to income within each of our groups, we end up with parallel lines. So we do not want any interaction, as I had mentioned previously. All right, so these are the conditions in order for us to make valid interpretation, and some of these conditions all of them are necessary also for valid inference, but some of them, the ones with the asterisk, are only about valid inference. So if we have those last three bullets, if we've met those conditions, we can interpret even though we cannot infer. If we've met all of the bullets, we can interpret and infer. So with that information under our belts, let's go ahead and proceed with what is called classical ANCOVA. That is, we have to assume there's no interaction of education and race. I say classical, I said classical ANCOVA, I mean classical ANCOVA, sorry. To proceed with classical ANCOVA, we have to assume there's no interaction of education and race. I say classical ANCOVA because there are more advanced methods that do allow for interaction, but they are outside of the scope of this course. And so we're going to put interaction in the ANCOVA table to see if we can infer an interaction, and we're hoping not. Now this is a little bit dicey, and I'll explain why. First thing I notice is something I'm happy to notice, and that is our sums of squares are not very high here for interaction. There is some, but of course you're always going to get some sums of squares just by sampling variation. So don't ever expect to look at that and see the sum of squares be 0. But you hope it's low. You hope the sums of squares is low, especially relative to the others. And I see, in fact, that the sum of squares is the lowest here for interaction relative to the other. And I also notice that there is a pretty relatively large p-value, especially considering the p-values that we want to see typically when we want to make inferences. Well, this is a case where I do not want to infer interaction. In fact, I don't want interaction. So I'm encouraged by both these things, and I'm going to proceed assuming that I have a model without interaction and that that model makes sense. Now, the reason I say it's a little bit dicey here is because when you have a high p-value, you have not shown that there's no effect. You simply have made a decision here to proceed as though there's no effect. Because remember that with small samples especially, we can have large p-values even when there is an effect. So you actually could have interaction in your population and then take out a small sample and not be able to infer interaction because of the variability of your estimate of interaction. So we're proceeding, because it's the best we can do at this point, we're proceeding as though there is no interaction. But in order for us to be able to make sense of the results, there really cannot be interaction of race to our education, to our covariate. Okay? So recall that what we're looking for is when we talk about what is the relationship of education to income, we don't want to say, oh, it depends on race. We want it to be the same for regardless of which race category that we're in. All right, I'm now going to check for both a linear relationship and homogeneity of variance as a first step in checking the conditions for valid inference. Now you say, why a linear relationship here when we have a categorical variable? Well, remember, we also have a quantitative explanatory variable, and that we do need a linear relationship for, the relationship of the quantitative explanatory variable with the quantitative response variable. So I'm going to check for linear relationship and homogeneity of variance, and I'm using the model that I'm going to use as my final model. That is the one that does not include interaction. You notice that that's education plus race, not education with an asterisk and then race, or times race, or by race, in which case that would be an interaction. So this is only looking at the two main effects, that of education and that of race on income. And then I'm going to save the output from a linear model using the LM function. And I'm going to plot, and I'm going to get the first plot that I can get with that output. And that becomes a residual fit plot, in which I am looking at the residuals as a function of fitted values. And I have two concerns going on here. Both of those conditions I'm concerned with. If there is a linear relationship, I expect that red line to stick pretty much right on 0. And notice it does take that little bit of movement up. I kind of expected that because if you look at this plot, doesn't it look like there's a little bit of a quadratic thing going on, a little bit of a curve, that a curve here would fit a little bit better than a straight line through these points. So I'm not that surprised to see a little bit of a curve going on here, meaning I don't have really a linear relationship. Now, it's not too bad. If I put a line through these points, that's not going to be real misleading. Okay, not as good as I could get if I put a little curve through, but not as bad as it could be. There could be some plots we could look at where if you put in a line, it would be really misleading. Here, it's not going to be that misleading. So I'm not quite as concerned about that, but I'm really concerned, as we've discussed before, about homogeneity of variance. And the difference here in this plot from the one we looked at way back up here, let's find this one, is that this only had the race in as the explanatory variable, while this one down here are the residuals for both race and education. That is, both of the explanatory variables are in the model. You can see the model right here. So I was hoping for more homogeneity of variance, but notice we have that what is considered a classical funnel effect, that if I were to try to take and incorporate all the points, I'd have to put a line up here on a diagonal and a line down here on a diagonal. It's like a funnel opening up. That means that the higher I get in terms of my projected income, my predicted income, the higher I get from left to right in my predicted income, the more variability I have. And again, I'm not surprised by that from a theoretical basis, the fact that when you get into higher incomes, there's a lot more variability than when you get into lower incomes. If you think about people making a minimum wage and they're in minimum wage jobs, well, they're all in those minimum wage jobs. They're going to make similar amounts of money for the same amount of work. Here, though, when I get into higher income levels, there's more variability. So let's check for the final condition for valid inference. Now, that's not for interpretation, that's for valid inference. This one, the no interaction, was necessary for both interpretation and inference. But this is just looking for inference, and also the normality one, in which I'm now going to do the second plot. That one is going to also deal with inference, and I see that right skew in that the distribution. See the points up here? So even though I'm looking better than in this lower tail than I did back up here when we did normality with just race back up here. Okay, it doesn't look as bad in that lower tail, but it still looks bad on the upper side. And so because of that, I'm going to end up not having correct p-values. So this is a problem as well with a heavier than normal upper tail. In short, we've not met the conditions for valid inference on almost all statistical fronts. I'm assuming independence of observations, but that's a design issue and I don't have access to that information. So this would be, if it wasn't a class, if it was not me giving instruction, this would be a good place to stop and not make inferences. As long as we meet the conditions for proper interpretation, we could go ahead and talk about what happened in our sample, but we can't proceed with inferences here. But then we wouldn't learn about ANCOVA, so I'm going to keep going. But I do want you to be aware that when you have these kind of problems here, the most that we're going to be able to do in terms of our p-statistics or our confidence intervals is to make some very rough approximations here. All right, so moving out, the one condition that did seem reasonable is no interaction of the extraneous variables. So let's go ahead and look at the analysis of variance for that model in which we don't have interaction. And we look at the analysis of variance that model and notice that our covariate is explaining for quite a bit of a proportion of the variation. The question now becomes, do I see differences in race that I can infer? Do I see the differences in race that I can infer given these particular data after taking into account education? We already saw that when we did not take into account education, that we had differences in the income for race. Would education alleviate that? Well, it turns out that if you're using a type 1 error rate of 0.05, you would not reject the null hypothesis. That doesn't mean you've proven that there are no differences. It's just you're not going to be able to infer differences. So we're not going to be able to infer differences here if we're using a maximum type 1 error rate of 0.05. But again, remember, this p-statistic is wrong, but I'm proceeding as though it wasn't wrong to show you what we would do if it was correct. Now, remember that we inferred an income difference when we ignored education. I'm going to put that ANCOVA table we already did up above. I'm going to put it down here again. So here we did make an inference, but after accounting for education, we did not. Now, that's only on inference. The temptation might be to say, so if you account for education, then that means that that's explaining the difference between the income disparities in race because we're accounting for education now. I don't want to make conclusions about income differences that are a result of the education differences. In the best case scenario, for this type of analysis, the education variable for our different participant groups would look identical, and then we would be able to say that, hey, yeah, it's not education that's making a difference here. And this would provide more power for detecting any relationship that there did exist between your race factor and your income. ANCOVA is a terrific tool when we can randomize to conditions and also measure a strong extraneous variable. Remember that. So even though I have an observational study here, if I can randomize to treatment conditions and a control condition and take into account an extraneous variable and do ANCOVA, that's beautiful. That's the best place to use it. Don't believe what you hear when people say, oh, ANCOVA is for when you can't randomize. No, you gain a lot of power when you can randomize. It's a terrific tool. But in the current example, we cannot possibly randomize. So I'm going to take a closer look at the education differences. So notice that the differences in education in our groups, even those that appeared relatively small, could be important. The main issue I detect when I looked at the scatter plot is with education inequality above, remember back here, above 16 years. Above 16 years. And I'm worried about making some extrapolation for especially Hispanic, but also for Black beyond 16 years, because I really don't have many individuals, if any, in that range. So what I'm going to do here is I'm going to take those out. So I'm going to do that right here. I'm going to do a revised income and look again at my ANCOVA and see what I get when I take out those. And it turns out that I still cannot infer a differences in income. So I reached the same conclusion as if we had left those points in. That doesn't mean this is perfect. There are still educational differences, yet I'm more comfortable going ahead and proceeding with the conclusion that I cannot infer racial or ethnic income disparities after adjusting for education. Now, does this mean that income is the same? Not at all. Remember that description in our sample is our best guess. But whether we can infer the results relies on stability, and that relies on such things as sample size. Let's look at the regression coefficients again for the equation we've been using. It's right here. Okay, these are the regression coefficients. So notice that we don't see the Black group up here. That's because it's being used as the reference group. These coefficients tell us that for the Hispanic group, we need to add 5.941 to the intercept, and for the white group, we need to add 10.874 to the intercept. So that's what I'm doing down here. So I'm plotting this again, but when I make my lines, notice what I'm doing. I'm taking the intercept here and leaving it as is for the black group. For the Hispanic group, I'm adding 5941, and for the white group, I'm adding 10.874. And when I do this plot, there's the picture. There's the ANCOVA, the analysis of covariance picture for our sample. We're not making inferences that the differences in these lines can be inferred. But nonetheless, we're also not saying those lines are on top of one another. If those lines were on top of one another, that would suggest to us that once you take into account education, there's no income disparity. But instead, what we've seen is that the average Hispanic annual salary is $5,941. Remember that 5.941 is $5,941 more than the average black salary, and the average white salary is $10,874 more than the average black salary. So our sample suggests disparities, and I would consider those substantial disparities even after accounting for years of education, because that's what we're seeing with those lines. If education wasn't making a difference, those lines would all be horizontal, but education is making a difference. Notice here that we're making that condition that I described earlier, that the lines have the same slope for each of the three groups, that they don't have different slopes. That's a different kind of ANCOVA than classical ANCOVA. In classical ANCOVA, they all have the same groups. So these are not stable enough estimates to be able to infer these differences between those lines to the population, but my best guess is there is income disparity. We created this model assuming no interaction, so we forced the lines to be parallel. That means that the difference in income are the same in this model, regardless of which years of education you choose. So if you choose down here for 11 years education, the difference is the same as if you choose up here for 19 years education. So what do we do when we want to report this? It's common to find adjusted means when doing ANCOVA. By convention, this is the mean of the response variable at the mean of the covariate. We already know that the difference in adjusted means when comparing to black is 5.941 for Hispanic and 10.874 for white. But we can use the regression coefficients to find the predicted value at the mean of education, our covariate. So notice what I'm doing here. For adjusted black, here's the intercept, 26.538. Here's the slope. But what I'm using here with that slope to make a prediction is the mean of the covariate, which is education. Similarly, down here for Hispanic, I'm adjusting the intercept by the same amount I did when I drew these lines up here. Same slope, okay? These slopes are all going to be the same, and I'm predicting at the mean of education, and then similarly for white. The rest of this is just all putting it together so that I can give you a nice little printout, and this is what the printout looks like. The adjusted means about $30,000 for black, $36,000 for Hispanic, and $41,000 for white. If we go up here when we did not include education and we look at the, let's see if I can find those descriptive statistics, it was 28, 31, and 42. 28, 31, and 42. Coming down here, it's about 30, 36, and 41. You actually should prefer that these adjusted means are not very different than the means that you had above, even though now you've been able to adjust based upon years of education. You're doing it at the mean of the covariate, so it should be similar to what you had above, because the reason they would be a lot different than what you had above is if you had interaction, and we don't want that. We don't want one group to be shifted above or beyond the other. I already explained that. I didn't like the fact that the white income out here was on like anything that we saw for Hispanic, and only one person that was black in this income level, and that was rather low. So that part there always troubled me, which is why I did that extra little ANCOVA table up here in order to see that I would still get a high p-value, and I do. All right, so this is really my best example now of here are the discrepancies. So what do I have there? Between black and Hispanic, about $6,000 per year. Between black and white, about $10,000 per year. Remember, it was higher than that when we did not account for education. So education accounted for some of the disparity, but it did not erase the disparities. How do you juxtapose that fact with the fact that we were not able to make inferences back up here? Where is it? Right here. We were not able to make inferences back up here. This was our ANCOVA table right here. And we were not able to make inferences. How do you juxtapose that with the fact we see disparity? It's because our estimates are not stable enough to make inferences. That's all. And that could be because of sample size. So you don't go around saying, oh, I could not make an inference, and therefore, once you adjust for education, there's no disparity. No, we see the disparity right here staring us in the face. It's just, can I make claims about this beyond this study? No, I need to do more study, and I probably need to take bigger sample sizes so that I can have more stable estimates. All right, so that's analysis of covariance. What I'm going to do in the next video is I'm going to wrap this up with a little summary, and then I'm going to take on a challenge in order to write a report, and it's going to be on this same topic, although I will tell you right now that a lot of what I did here in this little resource that I provided here, a lot of what I did is just teaching you. When I write the report, a lot of that won't be included in my report because I'm going to do a classical ANCOVA, that is a straight analysis of covariance without doing all these little teaching elements in there. So I'm going to grab a lot of pieces. Actually, all the pieces I need are in here, but I'm not going to be using them all in the same order when I do my analysis of covariance. So stay tuned for that in the upcoming video.